Hi all, welcome to my YouTube channel Know About Embedded System. In today's video, I'm going to explain and also I'll show you output how to generate square wave and rectangular wave using DAC. In the previous video, I have explained you about a DAC, that is nothing but a digital to analog converter. What is the DAC, why it is required, and how we can generate output using DAC. In today's video, I will show you practical. With the practicals, I'll show you output, how to generate the square wave and how to generate the rectangular wave using DAC. So let us start the video. Before starting the video, if you are a new viewer to my channel, please subscribe my channel and gain the knowledge on embedded system. Let us start the video here. Square wave and rectangular wave generation using DAC. So guys, we know that already. What is the DAC stands for? DAC stands for a digital to analog converter. So that means what is the input for DAC? DAC input is nothing but binary inputs. Binary inputs we have to give. So binary inputs we have to give in the input section, and the respective output it is going to generate according to the logic implementation. If you want square wave, we have to implement logic for the square wave, or if you want to generate a sine wave, we have to write a logic for generating a square wave, and if you want to generate a staircase wave, then that is also possible. So DAC, from the DAC, it is possible to generate all different waveforms which is required to control a different embedded system application in real time. So in today's video, as I told you, I'll show you two different examples. One is a square wave generation and one is rectangular wave generation. So what do you mean by square wave? Square wave, you know that already. I don't want to explain more here. Square wave means we will have the waveform which is having on and off period same. So this is your on time and this is your off time. So let us assume this is my on time and this is my off time. If you're having on period and off period equal, then that type of waveforms are called as square wave. We will write a code for generating square wave, and this is the square wave. And in another case, what do you mean by rectangular wave? Rectangular wave means it is having unequal on and off period, unequal on and off period. Okay, so here you can see, so this is my on period and off period is different. Okay, so let us assume this is my on period is different and off period time is also different. So whenever you have not equal or unequal on and off period, then that wave is called as a rectangular wave, or sometimes it's also called as pulse. So now let us go back to the code, and then we will develop the code for both the cases, square wave and rectangular wave. This red color, what you are seeing, this is a square wave and this is a rectangular wave. Okay, so now let us go. Before going to the code, I need to show you one important thing that is called as pin function selection. Already in the previous video, I have explained you what is a pin function selection. Today I'll show you one more use case, that is analog output generation. Here you can see the pin number I'm going to use, that is P0.26. In LPC 1768 microcontroller, one analog 10-bit DAC is there. In our LPC 1768 microcontroller, we have 10-bit DAC. 10-bit DAC is there, and we have one output that is called as A out. We have one output that's called as A out, and this analog output is mapped, A out is mapped to P0.26, and this P0.26 is mapped to analog output in a function number 2. Here you can see the function number 2, nothing but 10, is defined with an analog output. Now the pin cell register, you can see it is defined with pin cell 1. It is defined in pin cell 1, and bit numbers are defined with 20 and 21. So you need to develop the code in this way. So pin cell 1 is equal to function number 2 left shift of 20. So this is the code we have to write it in order to enable the analog output. Okay, so we will develop the same thing in the code later. Along with this, I have one more thing to explain about the DAC. So that is a register. Let us go back here. Here you can see chapter number 30. Chapter number 30 is a DAC chapter. So details they have given. I told you already, in our LPC 1768 microcontroller, we have 10-bit DAC, right? So you can refer this for your description if you want, and I'm going to explain only very few parts here. So this is what I told you just now. A out is nothing but analog output. Okay, so this uses 3.3 volts supply. 3.3 volt supply it will use, and it will produce analog output. Okay, and then along with that I need to go for one important register that is called as DACR. What do you mean by DACR? DACR stands for digital to analog convert register. This is one register, one exclusive register which is available for a DAC. Okay, here you can see. So this is the name of the register, DACR, that stands for digital to analog converter. Under this, some of the bits they have defined. My concern or my scope is defined only for bit number 60, bit number 6 to bit number 15. Your digital input. So digital input should be given between bit number 5 to bit number 6 to bit number 15. So whatever you give digital input, that should be defined between bit number 6 to bit number 15, and other bits we are not touching. Okay, so digital input, whatever you are going to give digital input, should be given in the DACR register between bit number 6 to bit number 15, and remaining bits we are not using at in this programming level. Let us go back to code here. I have already written the code, and I will show you what I have written and how you can also try in your local system. The first thing is I'm going to use P 0.26. 0.26 is nothing but analog output port pin. I need to produce analog output, and this analog output is defined in function number 2. Okay, so for that purpose, as usual, I have created a macros function selection 0, 1, 2, 3, and then I'm going to create one variable here, DAC input, and basic clock configuration I'm doing, and then I'm configuring P0. Line number 19, you can see here I'm configuring P0.26 as an analog output pin by using function selection 2 with a bit number 20 with a pin cell 1. Okay, so just you watch the video once again, then you will understand what is the meaning of this. So as I told already, when I say square wave means I should get on and off period both same. So off and on period should be same. That's why. So what I'm doing, I'm initializing 0 and FF. So this is my FF. This is my FF 0 FF. So the high means 0x FF, and low means it is 0x 00. I'm assigning two different value, FF and 00. FF and 00. So the same thing you can see in the code as well. Here you can see DAC input I'm assigning 0, and then DAC input I'm assigning as FF. So two inputs are required, FF and 00, to generate the square wave. Next point, here you can see line number 24 and line number 28. So here I'm loading, this is a variable, DAC input is a variable here, and this variable I'm pushing into bit number 6 to bit number 15. This is what I told you in the DAC explanation, DAC theory register. Here you can see. So this is called DACR register, and here I need to assign the value. So digital value I should load between 6 to 15. That's what I'm doing here. Digital input is pushed between 6 to bit number 15. Okay, and I'm multiplying by 4. That is because I have 10-bit DAC. That is why this 8-bit value I'm just multiplying by 4. So when I multiply by 4, it will be getting converted into 10-bit. Okay, so just you can keep in mind, I'm giving a 0 and FF, and then I'm giving input to the DAC. So here delay I'm keeping both are same. It should produce a square wave. So let us check whether will it produce a square wave or not. I'll save the code and then compile it, and then go to debug window. So here so this is my register called as the DACR, and this is my logic analyzer. I'll tell you how to open this. First I'll remove all. Okay, so here you can see this is a logic analyzer. Usually it will be available here. If it is not visible here, you can click it here and press on logic analyzer. Logic analyzer will open, and then go to setup here. Go to setup, and you can just add insert logical analyzer signal. You just click on this and you can write A out. A out stands for analog output. Just enter. Now you can see here my A out signal is mapped into logical analyzer output, and you can keep better 4 because your input for a DAC, the reference voltage for a DAC is 3.3 volt. So better to take 4 volts, minimum 0, maximum 4. So you can take 0 to 4 instead of 5. Just after that, setting all, just you can close it. And after this, you can just give one run. So just apply run button here. You can see I'm able to generate square wave. So how can I say it is a square wave? Because it is getting on and off period same. If you measure very clearly, if you want, you can set up the same code and you can run in your local system. Measure the time unit of on and off period. It will be same only. So why it is same? Because in the code we have written delay same. Here you can see line number 25 is given with 100 delay, and line number 29 also is given with 100 delay. So since we are giving a delay with the same for on and off, it is going to generate the square wave here. So this is a square wave. Okay, so if you want, you can set up and you can try whether it's a square wave or not. So this is the first output I wanted to show you as a square wave. And second output or second program what I wanted to show you today is rectangular wave. So what do you mean by rectangular wave? So you know that already. Rectangular means, so on period will be more and off period will be less. On period will be more and off period will be less. So like this, you will get a wave with a maximum time of on period and minimum time of off period. That type of waves are called as rectangular waves. Let us try that as well. So very simple code change. What is the code change? Output 0 is there, no? There you can reduce the delay. Approximately 20 or 30 you can give. And for on period, let it be 100. For on period, let us give 100. And then let us try this and let us check the output, whether will it work or not. So same thing, just keep it logical analyzer here. Yeah, now you can see here on period is more and off period is less. Correct, right? This type of output waveforms are called as rectangular waveform. This is also analog. There is a difference between square wave and rectangular wave, and there is a difference between square wave and digital bits. Digital bits will have only zeros and ones, but in case of analog square wave, high and low will be there, and that high and low timing period you can change it. But in this use case, currently what you are seeing, this is called rectangular wave. In the rectangular wave, output on period will be more and off period will be less. So, and also you can see here the output analog voltage, it is changing between 0 to 3.28. So this is the reason I told you to take here the F4 as a maximum value. Okay, and the reference voltage is 3.3, so your output should not go beyond the 3.3 volts. Right, I hope this video is interesting to all and you like this video, it seems. So with this, I just want to end my hit the like button and subscribe my channel and gain the knowledge on an embedded system. So we'll meet you in the next video again.